Do you think the hardest part of building a bridge is finding a spot for the piers and pouring concrete? How about driving the piers into the bottom of a gorge 350 meters deep? It's as if you were stacking two enormous skyscrapers on top of each other. Now imagine having to hoist steel blocks into the air. Each block weighs 90 tons. That's heavier than a massive passenger plane. Today, we'll rise above the Tarn River Valley in southern France. You'll see how 13 years of calculations and 3 years of construction turned an impossible task into a bridge that literally soars above the clouds. You'll learn why a special type of asphalt, one that simply didn't exist before, had to be invented for this structure. And by the end, you'll understand why the engineers who built it weren't sure until the very last minute that everything would work out. Ready to take a bird's eye view? Let's begin. Every summer at the end of August, the same thing happened in the south of France. Thousands of cars carrying tourists traveling from Paris to the coast or to Spain would converge on a single point on the map. That point was the small town of Millau in the Tarn River Valley. The road ran right through it, and there was simply nowhere to go around it. On peak days, traffic jams stretched for 20 kilometers. People sat in their cars for hours. Trucks carrying goods were delayed by a day. Buses full of children stood motionless under the sun. Highway A75, which was supposed to connect Paris with the south of France, had been under construction since 1975. For 30 years, the road was built kilometer by kilometer. But as it approached Millau, it ran into the Tarn River Valley, wide, deep, with steep rock walls on both sides. Here the highway came to an end. No one knew how to span the valley. It was easier to drive through the city and get stuck in traffic. The engineers understood. A bridge was needed. But the valley was so wide and deep that a conventional bridge wouldn't work here. The distance between the two banks is nearly 2.5 kilometers. The valley floor lies 270 meters below the road level. It's like putting the Eiffel Tower in a pit and still leaving several stories above ground level. No one in the world had ever built a road bridge of that height. In 1987, the French government officially began research. Not construction, not design, just research. Just to understand whether it was even possible. Geologists studied the valley floor. Meteorologists measured the wind. Mathematicians built models. 13 years passed. During that time, governments came and went, budgets changed, and opinions shifted on whether the bridge was even needed. Opponents said it outright. Too expensive, too complicated, it would never pay for itself. Supporters countered, every summer the valley loses millions of euros due to traffic jams, and tourists leave angry and exhausted. The debate dragged on, and the traffic jams continued. But it was during these very years, in different corners of Europe, that two people who did not yet know each other were working on tasks that would later come together into a single project. One of them was a French engineer who had already built one of the longest cable-stayed bridges in the world. The other was a British architect whose name was already on buildings in dozens of countries. And when they were finally brought together, they proposed something that left officials speechless at first. By that point, Michel Virlocho had already built the Normandy Bridge, a cable-stayed bridge across the mouth of the Seine, which at the time of its opening in 1995 was the second longest cable-stayed bridge in the world. He knew how to calculate cables, how to distribute the load, and how to make steel bear the load at great heights. Norman Foster was the architect of a different kind of structure.
He thought not only about how a structure held up, but also about how it looked.
He was responsible for the renovation of the Berlin Reichstag, as well as dozens of airports and office complexes around the world. He knew how to make big things beautiful. Together, they proposed a cable-stayed bridge. This means that the roadway does not simply rest on supports, but hangs from steel cables that run diagonally from the supports down to the roadway. The supports function like masts. They hold the cables, and the cables hold the road. This design allows for very long spans between supports. There's no need to place a support every 20 meters. In the case of the Millau, each of the 6 central spans stretches 342 meters. That's a distance the average pedestrian covers in 4 minutes. 7 supports, 8 spans, total length 2,460 meters. The roadway is 32 meters wide, 2 lanes in each direction. The tallest pier was to reach 245 meters from the valley floor, and including the pylon above the road, 343 meters from the ground. That is 19 meters taller than the Eiffel Tower. When these figures were presented to the government, the reaction was muted. The project was estimated to cost 400 million euros. There was no public funding available, so they came up with another plan, a concession. The French government grants the right to build and operate the bridge to a private company. The company builds it with its own funds and then collects tolls for 78 years. After that, the bridge is transferred to the state. The company that took on this project was the Eiffel Group. It included Gustave Eiffel's workshops, the very same ones that built Paris's iconic tower. The connection to Eiffel was no coincidence. The Millau Viaduct and the Eiffel Tower were the only structures that this group built from scratch as the main contractor. On December 14, 2001, the cornerstone was laid in the Tarn Valley. 3 years of work lay ahead, and almost immediately it became clear that the most difficult part wasn't the height, it was the valley. The Tarn River Valley isn't just a pretty postcard landscape, it's a place with character. In the summer, it's hot and sunny here. But within a few hours, the weather can change completely. Clouds gather over the valley, the temperature drops, and the wind starts blowing down from the plateau. Not just a fresh breeze, but a real gust that knocks you off your feet. Officially recorded wind speeds in this area reach 200 kilometers per hour. That's a speed at which an ordinary person cannot stand upright in an open area. For the builders, this meant one thing. Every workday could be interrupted at any moment. You can't raise a crane in such winds. It's deadly dangerous. You also can't assemble steel sections in the air during gusts. Work had to be stopped regularly. The schedule was in shambles, but the engineers had anticipated this in advance and factored the time losses into the plan. The second problem was underground. The valley floor is not a level surface. The rock formation varied in hardness and composition at different points. Geologists spent several years drilling boreholes and taking samples to determine exactly where to place the supports. Each of the 7 supports ultimately stands on 4 boreholes, 15 meters deep and 5 meters in diameter. It's like driving 4 deep stakes into the ground under each leg of the bridge. Only after that is the foundation poured, and only then do they begin to raise the support itself. But the main engineering challenge lay elsewhere. Erecting the supports is a relatively straightforward task. Any builder knows how to pour concrete from the bottom up. The real challenge was something else: how to subsequently lift thousands of tons of steel trusses to a height of 270 meters and assemble them there into a single structure. No crane of that size exists. It is impossible to lift 90-ton blocks by helicopter. Building scaffolding from the ground up at such a height is a separate project, comparable in complexity to the bridge itself. Something else had to be devised, and the engineers came up with a solution. The solution chosen by the builders is called a sliding method. The concept is simple, but at such a height, it becomes something fantastic. The bridge deck isn't built on the ground or lifted by cranes. It's assembled on the shore, at road level, and then slowly pushed across the valley, horizontally, through the air, until it reaches the other side. Imagine this. You're putting out a desk drawer, except this drawer weighs 36,000 tons and hangs over a 270-meter deep chasm. The company Eiffel manufactured 2,200 steel deck sections. Each section weighed up to 90 tons, and some were as long as 22 meters. All parts were cut with a laser and a plasma cutter with precision down to fractions of a millimeter. The slightest misalignment and the two sections simply wouldn't fit together at that height. On the ground, this can be corrected. At a height of 270 meters, it's a disaster. The push was carried out simultaneously from both sides, from the north and south banks. 4 hydraulic jacks were positioned at each support, pushing the deck forward. The speed of movement was 150 millimeters per minute, roughly 1.5 centimeters in 60 seconds. For a structure weighing as much as several hundred fully loaded freight trains, this was the only feasible pace. Too fast, and the deck begins to vibrate. Too uneven, and the load is distributed incorrectly. To prevent the deck from sagging while moving over the span between supports, a special cantilever was attached to its front, a rigid metal nose that extended forward and was the first to locate the next support. It was this nose that absorbed the impact of any misalignment. To provide additional support for the long spans during movement, temporary supports 170 meters high were erected. They were welded from steel pipes and served only for the duration of the push, after which they were dismantled. Each such temporary support had to withstand a load of 7,000 tons. The entire process was monitored using satellite navigation. Every point along the deck was tracked with millimeter precision. If the deviation exceeded the permissible limit, the system stopped the jacks automatically, not via an operator's command, but on its own. Because at such a height, the cost of an error is too great to rely solely on human reaction. On May 28, 2004, the two ends of the deck, which had been moving toward each other from opposite banks, met over the Tarn River. It was the moment the entire team had been waiting for more than 2 years. The connection was officially announced that same day, although technically the final welding took several more days. The engineers standing down in the valley and looking up saw only a thin steel strip suspended above them in the sky. One of the construction workers would later say, "No one went home that day. Everyone just stood there and watched." But even after the span was in place, the work wasn't finished. One task remained, which at first no one took seriously, but which then dragged on for 3 years. It would seem that after 7 skyscraper-tall supports were driven into the rocky bottom of the gorge, and 36,000 tons of steel were hoisted through the air to a height of 270 meters, what could be so difficult about laying asphalt? It turned out that this was precisely where the engineers faced a challenge that had never been solved anywhere in the world before them. Ordinary asphalt doesn't work on a bridge like this. The fact is that a steel deck behaves differently than the concrete foundation of a regular road. Metal expands in the heat and contracts in the cold. At an altitude of 270 meters, the temperature fluctuations between winter and summer and between night and day are much more extreme than at ground level. The bridge deck is constantly moving, just a little by millimeters, but it moves. Standard asphalt concrete cracks under such movements. Chips begin to appear, water gets inside, and the metal beneath the pavement begins to rust. Repairing a road at a height of 270 meters is a separate, costly operation that we would prefer to carry out as infrequently as possible. The requirements for the pavement were contradictory. On the one hand, it had to be soft enough to move with the metal and not crack. On the other hand, it had to be hard enough to withstand truck wheels without deforming. In addition, the pavement had to be water-resistant, non-slip, and capable of lasting as long as possible without repairs. None of the existing mixtures at the time met all these requirements simultaneously. Work on the formula for the new asphalt proceeded in parallel with the bridge's construction and took nearly 3 years. Experts tested various mixtures, adjusted the proportions, and evaluated samples in laboratories and on test sites. The final material was deemed unique. Its formulation had never been used anywhere else in the world in this form. This pavement was developed specifically for one particular bridge and for nothing else. The layer of asphalt on the Millau Viaduct is thinner than on a regular road, but it works differently. It sort of floats on the metal, following its movement, while remaining strong under load. This fact almost never makes it into tourist brochures. They write about the height and records. But the people who worked on the construction site say that the asphalt challenge was one of the most grueling of all time. Because a mistake here isn't immediately visible, the pavement could look fine for a year, 2, 3, and then start to crumble from the inside. It was impossible to fully verify this in advance. They had to make a decision based on calculations and lab tests, knowing that the pavement would only pass the real test under actual traffic. Today, more than 20 years after its opening, the asphalt on the viaduct is holding up. It has never been replaced. That in itself shows that the calculations were correct. And so, by the fall of 2004, the bridge was almost ready. The supports were in place, the deck was suspended, the cables were tensioned, the pavement was laid. Only one thing remained, the load test. And it was this test that revealed something unexpected. While the builders were working in the valley, the controversy outside did not subside. The project had many opponents, and they were not silent. Organizations that opposed the viaduct filed complaints, demanded expert assessments, and appealed to officials. Their arguments went like this: the bridge is too heavy for the gorge's bed. The soil there is unstable and will eventually settle. A 78-year concession is too long. The state will lose control over vital infrastructure. The new highway will bypass the town of Millau, and local merchants will lose customers. Money is being wasted on a road that leads to tiny Béziers. The last argument was particularly forceful. Route A75, of which the viaduct was the final link, connected Paris with Béziers. Critics asked, who even goes to Béziers? Why build an expensive bridge for a route used only during vacations? Supporters replied, through Béziers and beyond, the road leads to Montpellier, to the Mediterranean Sea, to the border with Spain. In the summer, this route carries a huge volume of traffic, and in the winter, it will serve freight transport, which currently has to make a detour of hundreds of kilometers. The debate ended not with arguments, but with a fact. The bridge was built. In November 2004, a load test was conducted. Several convoys of heavy equipment drove onto the deck, exerting a total pressure of 920 tons on the bridge. Engineers monitored the readings from sensors on the supports, the cables, and the deck itself. Sensors were installed at hundreds of points across the bridge and operated in real time. The results matched the calculations. The deck's deflection under load was within acceptable limits. The bridge behaved exactly as the formulas on paper had predicted. It was a rare moment in engineering when reality matched theory almost exactly. On December 14, 2004, the bridge was officially opened. The date turned out to be symbolic. Exactly 3 years earlier, on December 14, 2001, the cornerstone had been laid. French President Jacques Chirac attended the ceremony. He walked across the bridge and uttered words that were later often quoted. France knows how to do things that seemed impossible. The bridge was opened to traffic 2 days later, on December 16th. According to the plan, the opening was scheduled for January 10, 2005. The builders finished nearly a month ahead of schedule. As a result of the construction, the Millau Viaduct earned 3 entries in the Guinness Book of World Records. The first record is for the world's tallest pier. Pier R2 reaches 245 meters from the valley floor. Prior to this, the world record was held by the German Cockatall Viaduct, which stands 181 meters tall. The second record is for the world's tallest pier and pylon structure. The same pier, together with the pylon above the road, reaches 343 meters. The third record is for the world's highest road deck above ground level, 270 meters. All 3 records were broken by a single structure in one location. 2 years later, in 2006, the viaduct received an award from the IABSE, the International Association for Bridge and Structural Engineering, which awards its prize to the world's best structures. Critics who had claimed that no one needed the bridge had by then already seen the initial traffic figures. People were driving across the bridge, in large numbers. But the most unexpected thing that happened after the opening had nothing to do with records or awards. It was fog.
There is one phenomenon that was not anticipated by the project and is not described in any technical documentation. Several times a year, especially in the fall and winter, the Tarn Valley fills with fog. A thick, low fog that creeps along the valley floor and obscures everything below a certain height. On such days, drivers traveling along the viaduct see something unusual. The supports extend downward and vanish into a white cloud. The ground is invisible. Other cars below are invisible. It seems as though the road is simply hanging in the air on its own, without any support, between the two walls of the plateau. The view from below, from the valley, is no less strange. You can see the upper part of the supports and the road surface, and beneath them, only white cotton wool. The bridge seems to be floating. It is precisely this effect that has made the viaduct a tourist attraction. People come specifically to see it. 7 viewing platforms have been set up around the bridge, on different sides and at different levels. One of them offers a view from below, directly under the bridge, from where you can see the full height of the supports and the cables fanning out toward the roadway. From another platform, located at the level of the road itself, you can look along the deck, and then it seems as though the bridge stretches straight into the horizon. The town of Millau itself, which suffered from summer traffic jams before the viaduct opened, now welcomes a different kind of tourist. Not those who got stuck in traffic and wandered into a cafe out of boredom, but those who came specifically to see the bridge. Tourism in the area has grown significantly in the first few years since the opening. Those who said that the new route would kill commerce in the town were wrong on both counts. Cars no longer drive through the town, but people come here with a specific purpose. As for the bridge itself as an engineering structure, it is designed to last 120 years. Eiffel's concession will expire on December 31st, 2079, after which the bridge will be transferred to the state. If traffic exceeds projections, the French government may take over the bridge earlier. This right is stipulated in the contract. For now, the bridge is operating normally. About 3 million vehicles cross it annually. Sensors are constantly monitoring the supports and cables, recording loads, vibrations, and displacements in real time. If any indicator exceeds the normal range, the system issues an alert. So far, there have been no serious deviations during all these years of operation. The bridge is performing exactly as designed. This is rare in itself for a structure of this scale. Many large-scale projects begin to present surprises after opening. The Millau remains silent for now. An interesting detail, the bridge is slightly curved in plan view. When viewed from above, it does not run strictly straight, but has a gentle curve with a radius of 20 kilometers. This was done intentionally so that drivers entering the bridge can see it in its entirety and assess where they are going. A straight bridge 2.5 kilometers long, spanning the valley, would have a more oppressive psychological effect. The slight curve creates a sense of perspective and makes the approach more comfortable. Such factors were taken into account during the design process alongside load calculations. The Millau Viaduct began as a solution to a simple, practical problem, eliminating traffic congestion in the south of France. For 30 years, an unfinished road had come to a dead end in the valley, which could not be crossed by conventional means. 13 years of research, 3 years of construction, 400 million euros, and several thousand people who climb to a bird's-eye view every day to work. The result is a bridge taller than the Eiffel Tower, longer than 25 standard soccer fields, and supported by piers driven 15 meters into the rock at the bottom of the gorge. A new type of asphalt was invented just for it. Temporary supports as tall as a 50-story building were erected for it, and then dismantled. No one needs them anymore. 36,000 tons of steel were hauled across it at a speed of 1.5 centimeters per minute. When you look at the viaduct from below, from the valley, on a clear day, the supports seem thin, too thin for such a height. And on a foggy day, when clouds cover the base of the supports, the bridge truly hangs in the air, with no ground beneath it, no visible support. Just a road between two banks,
at a height where only birds used to fly. If you found this story interesting, give it a like, subscribe to the channel, and click the bell icon. There are many more stories ahead about things that seemed impossible and were built anyway.